All right, again, welcome to a Sunday session. So we're going to continue on talking about multi-boson physics today, and then we'll go into the final subject of Higgs physics. So we went a little bit long yesterday, so we're going to go a little bit short today, but see how it goes. All right, so we talked, let's go back one yesterday. From the beginnings of multi-boson physics, we talked about diboson, the sort of simple production of dibosons, the same for tribosons. So it's not actually the most interesting area of multi-boson physics. The most interesting area, I'd say, is vector boson scatter. This is where we hope to learn some fundamental things about the standard model. And also we'll see on the cross-section map here, it's sitting down here at the lowest cross-sections measured by the LHC experiment. So in fact, this ZZ cross-section here is a fraction of a femtobarn. So as I was saying, cross-sections now small as some of them a femtobarn, some of them a fraction of the femtobarn. That really means it takes LHC luminosities to do these sort of measurements. So if you imagine if we have 100 inverse femtobars, that makes it simple. Then if you have a 0.3 femtobarn cross-section, that means you only get 30 events in that data set. And that's a quite large data set, though now in run 3, we're moving on to even larger data sets where we're going to be getting hundreds of events in analysis, is like that. So vector boson scattering is a purely electroweak phenomenon. So you can see every vertex in these diagrams here involves some sort of electroweak coupling. So the emission of W bosons here, they're scattering by a Z boson, and then you form W bosons again, and then they decay photonically. So every vertex, an electroweak vertex. And so there are multiple diagrams that can do this, ending in the final state. This is sort of a typical case where you have 3. And so you notice there's a scattering by a vector boson with 2 TGCs here, a quartic gauge coupling, something pretty much uniquely can be seen in these sort of interactions. You can take 3 vector bosons via a quartic coupling, but it's really difficult to observe that if we ever really can separately. And then the most interesting diagram here is the scattering via the Higgs boson. So sort of famously, and one of the reasons people thought there must be a Higgs boson, if you calculate these cross-sections by themselves, so it's an exercise that you could probably do with 10 pages of paper or something, and it converges pretty quick because it's all electroweak. You don't have to go to higher orders. So it's possible. But you find that not only does the cross-section go up, it goes beyond the unitary limit. So you'd be making more than you actually have collisions. It actually goes to infinity as you go upward in energy. And it's only the existence of this Higgs diagram that gives interfering contribution that ends up with a finite cross-section. So that's very interesting because if I put anything else here, let's say some heavy Higgs boson, I better still have that cancellation to get a finite cross-section, but it's very sensitive to that. This is a great place to look for new physics. A new vector boson or Higgs boson there means that you would see a significant deviation. So as I was saying, these production diagrams, they can have these double TDCs, quartic gauge couplings. You can have Higgs scattering. It can be these things can happen in the S and T channel, depending on which mode you're looking at. And then to make it all more complex, there are interfering QCD diagrams where you also get the 2 vector bosons plus 2 quarks in the end state. And in general, it's not so easy to actually differentiate these 2 things. So when you're seeing vector boson scattering and when you're seeing these QCD interactions. So we've been analyzing this ever since, even the ATV runs of the LHC, but it was first discovered in 13 TV data and observed in this W+, because it's very distinctive signature mode by the CMS experiment. So where are we now? we're observing the lowest cross-section processes here. And so ZZ is the most difficult of these to measure. It has cross sections with a fiducial selection of something like 0.33, the 1 inverse femtobarn. And so it's really not worth talking about a total cross section here, because in most of the region of phase space, the interference with the QCD diagrams can be so strong that you can't really differentiate that you're seeing electroweak scattering. But you can isolate a phase space where you see very forward jets and you see higher PT vector bosons that then is dominated by vector boson scattering. So we can make a fiducial selection and get a region that's like 95% vector boson scattering. So you isolate that region and you do an analysis, and then you can make some decisions. Atlas, for instance, in this analysis made the emphasis on maximizing the acceptance. CMS made an emphasis on the purity of the selection, so both against the QCD process, but also very well identified leptons and leptonic decays. And you can see that both can see a pretty obviously significant signal. But it turns out the Atlas bet was a little bit better. This is the one that led to the observation of this process, 5.6 sigma. The CMS analysis is 4 sigma. You can see there's still a pretty obvious signal there. So in fact, there was a factor of 4 between the two optimizations, with CMS going after signal that was fraction of an inverse femtobarn and Atlas a little bit over 1 inverse femtobarn. But both measurements very consistent with the standard model. So you'd have to search through everything, and there's some very unusual processes that we've looked for at LHC, but in any graph you tend to make, this is the smallest cross-section that LHC has measured, especially of a very physically interesting process. So with the measurement of that, where are we? So these are the Atlas results, and these are the CMS results. Atlas puts tri-boson and Higgs interactions here, so it's the bottom, that's vector boson scattering. For CMS, it's sort of from here down, that's vector boson scattering. You can see we have a lot of measurements, some with very big errors, some with smaller errors, but in general, we see agreement overall of them, where the measurement is sort of far from the expectation, error bars are large to match. In very small print, can't really see here all the numbers for the Atlas measurement, but they're also the comparisons that we've made, and that they're generally all to just NLO cross sections. So here it's purely electroweak, so they converge very quickly. You just need to understand what sort of extra initial states there are, and NLO gets you pretty much a good enough cross section calculation. Also, it's extremely hard to do at NLO. You're trying to calculate a process with 2 jets added to it that has QCD and electroweak contributions and large interference between them. So there's actually not an available NLO calculation that has been made yet. So these are the best that we have to offer. But on the other hand, we're making measurements now at sort of the 10% level. So NLO is really good enough for those comparisons. But hopefully we'll get eventually to the region where we're making percent level comparisons, and we'll have better predictions by then to make comparisons. So what do we want to do next? Well, we really want to analyze polarization. So because of these diagrams, for instance, involving Higgs scattering, you expect an interesting pattern of polarization that the Higgs will couple clearly to the longitudinal modes of the vector bosons. That's where they get their mass, for instance. You even expect an energy-dependent pattern, because which of these diagrams makes a larger contribution changes with energy, and so you expect an energy-dependent pattern of what the polarization is. We'd like to see that eventually. Also, you'd like to measure polarization, because if there was new physics there, if it's new physics coming from scalar bosons, you would expect maybe an excess and longitudinal polarized vector bosons here. If it's from instead some new Z boson or a W boson, a Z prime or a W prime, you might expect more transversely polarized vector bosons. So the only analysis that this has been done somewhat successfully in is the one with the largest signal and the most obvious final state, the W plus W plus. So with W's, you get a larger signal, slightly less because of the same sign, but the same sign really gives you a very distinct signal that doesn't look like anything else in the standard model. So this was actually also, you notice this for the state that was used for the first observation. So these are sort of our most sensitive state in terms of statistics because of that distinctive same sign final state. The QCD background is less here. It's harder to make same sign vector bosons in a QCD process compared to some of the other modes where there's a charge balance between things. But in order to try to spot longitudinal polarization, you really need a multivariate discriminant. So what you'd eventually like to do here is actually show two longitudinal vector bosons at once. This is the process that makes the contribution that makes the overall cross-section finite, and finite is a function of energy. But we're not quite there yet. That's really an HLOC application. What we can do instead is try to observe greater than or equal to one longitudinal boson. So events that either have one or they have two. So it could be either of the two for the one, or then there would be both longitudinal. And summing those up, we can see a significant signal. So here you can see the Atlas analysis, and then the light blue here is a transverse plus a longitudinal, where the darker blue here is the longitudinal and the longitudinal. So those are the contributions as depicted by Monte Carlo. And you can see that we generally see an excess that indicates that those contributions with longitudinal cross-section are there. So here again, we see at the evidence level, so 4.1 sigma, a signal with at least one longitudinal boson, and it's again a sub-femtomorph signal, so 0.88 in this case. And then you can put a limit on how much longitudinal you see. It's at 0.45, and that's not so much above the current standard model expectation. So you can imagine, let's see, with a factor of 2 or 4 more data, somewhere in between there, we'll get down to the standard model expectation. Maybe we're starting to see an excess, but we'd have to probably go several more factors, something like a factor of 10 beyond that, to get to the level where we can make evidence or an observation of the standard model. So again, HLHC application, but maybe something we're doing partway through the HLHC. This would be the first place that we'll look for that. And then I'll point out again that this is something that we can only do using a multivariate discriminant, and it has to be one of the more advanced variants, like a deep neural net in this case. We can't really do this by, for instance, just looking at the polarization distribution itself. You have to look at the polarization distributions, the angles relative to the vector boson flight direction. You have to look at the patterns between the two vector bosons, the rapidity gap between them, for instance. You have to look at the energy, because you expect this energy-dependent behavior of the polarization. It's really only the sum of all these variables that allows you to pick out an evidence level signal here. All right, so let's now go into the subject of Higgs production. So we're going a little bit back on the cross-section diagram here, but we're also at least staying even, if not going up a little bit, in the level of interest of what we're looking at. So the first subject I have is Higgs production and decay. So we're past observation now, but not by that many years. We have a lot more data on hand, and so we're starting to make more accurate measurements, but it's also very interesting in Higgs to sort of get a global picture of all the different interactions that are happening in order, because we think it's a place we might look for new physics, to get the global picture and see where there might be deviations. And so there are various approaches that have been gone after here. So there's sort of a highest level approach. So the Higgs couples to the vector bosons according to electroweak symmetry breaking parameters. The Higgs couples to each of the fermions according to its mass and what the Yukawa coupling is. And so you can make sort of a global picture where you respectively for the fermions and the vector bosons talk about what the coupling is, and you have to do it slightly differently, and then plot them on a linear scale that demonstrates how these things vary proportionally with mass. And so in these plots, we can see we go all the way from relatively small masses of the muon up to the larger mass of the top part. And we see a coupling that absolutely runs as we expected from electroweak symmetry breaking and as we expected from the Yukawa couplings. So let's digress a little bit on the Yukawa couplings. So it says that it's possible to introduce into the standard model a coupling. It doesn't break the gauge symmetry and so on. That gives you mass for the fermions. So these are the so-called Yukawa couplings. And sort of an interesting thing there is that you would generally expect them actually to go from 0 to a maximum of 1. The system is sort of set up so that's the range that they're supposed to be in. And we really sort of see that this is down near 0 comparatively, many orders of magnitude down on the scale, which would be even more orders of magnitude down for the electron if we could access that one. And it goes up on the other end, right up to 1 pretty much. And I think Reinhard in the previous lecture said that he felt that the top quark was very special. For me, actually, the thing that I always see as the most special about it is that it has this Yukawa coupling that looks like it's 1. And that sort of indicates a special relationship between the Higgs and the top. There are lots of models that try to do that. For instance, ones that say that Higgs and top are both composites in some system of binary particles, for instance. So instead of a U and a D quark, you have some technicolor particle or something that then these are bound states. They're the Higgs and the top, and that's why they would couple to each other mass and what. So we haven't found any new physics along that line, but I think it's pretty unambiguous that there's something very interesting about the top quark that has this unitary Yukawa coupling. And so here at that high level, we can see really perfectly that expectation of the coupling seen. So that probably means that we need to go beyond the high level to understand more. And so the next thing would be the data that goes into all these measurements, all the fiducial cross-section measurements. Cross-section is important because, for instance, the Higgs is coupling to the top in the classic triangle diagram where we have gluons come into a top triangle. In WZ or W Higgs or Z Higgs, there's a direct W or Z coupling there. And then decay branching fractions are important. You have the Higgs to WW, you have the Higgs to ZZ, you have the Higgs decays to the fermions accepting the top quark. You directly measure the couplings there. So that's the detailed data that goes into making this chart. So the next level would be to get more nuance to that. As for instance, divide up the phase space more, all the different production modes, instead of just the major ones, looking at various regions of PT or number of jets or other things that might be associated with different sorts of physics. And so this is the so-called simplified template cross-sections. You basically look at this unique cross-section regions, non-overlapping, and there's an agreement between the two experiments, Atlas and CMS, via the top working group on how to define those, so we can then be making the same measurements to make them comparable. So these working groups are incredibly important. The Higgs and top working groups, the electroweak working group on the head of the electroweak working group, actually, because then they define methods that we make this analysis so that two experiments can be comparable. And the one idea of science is that you want to be able to discover something, but then also reproduce it. Reproducibility is incredibly important. So having the two experiments, but also having these agreements that we can make measurements of the same exact properties so they can be comparable is very important. So we'll see that in these STXS cross sections, for instance. And then you can look at another most detailed level, which is fiducial cross-section measurements versus any property you might be interested in. For instance, the momentum or the PT of the Higgs boson, always looking at the high momentum region as a potential place to look for new physics. So here's the same plot from Atlas, and then we can see nicely illustrated at the bottom here, those smallest cross sections, the ones for the second generation particles. There, we'd really like to get a measurement to show that not only does the Higgs couple to the most massive particles, third generation ones, but also the next generation ones also. We can't get really the first generation particles. It's unclear whether we'll really ever have the accelerator to do that. But we should be able to get the second generation particles and are already pretty far along for the muon. All right, so that top level the detailed data under that quad top level analysis. So again, that is the different decay modes and the different production modes. So often glue and glue to H and BBH are put together because it's all things that are coming out of the PDF of the proton, and then we have vector boson fusion, the various associated productions, and then separately associated productions with two tops and a Higgs and a top and a Higgs. So looking at these plots here, we notice really the only significant deviation is maybe in this TH process. Then looking at the various decay modes, we see they all pretty much agree. There's a deviation here in WW. Both of these deviations, if I extend this error out to 2 sigma, would not look too exciting. In fact, specifically, maybe I'd call this one out because we'll see this deviation again in various places. I was looking for a plot, but I couldn't find it. There's an interesting plot from run 1 Tevatron, which shows the cross sections for top production. And you notice that initially you see a high cross section, and then it goes down and gets to the point where it matches the expectation. And this is sort of a well-known bias in Hep physics. And you can think about it in various ways, but my preferred way to think about it is that people are doing analysis, looking for something new. If they see it, they publish. If they don't see it, they integrate more data and see if they can see it next time. And so your initial measurement is essentially over the threshold almost every time. And so I really wouldn't necessarily take these T Higgs excesses to be too exciting at the moment. All right, so then we go down to this next detailed level. So one of my favorites, these STXS cross sections. So these are cross sections in various areas of phase space. So here it's broken out, for instance, by the PT of the Higgs. In other cases, it might involve extra jets or extra particles like the top here and so on. And then we make measurements in all those different areas of phase space. Of course, we can integrate them all together again into the various production modes equivalent to the previous page. You can then confirm that against other measurements you've done, for instance. Here's the one from CMS. Interestingly, we see excesses in associated production, and again, T Higgs. So that's at least one level more exciting. Now we see an excess in both experiments in T Higgs. But again, it's not a huge excess, especially in the log scale. It's sort of a little bit difficult to evaluate how many sigma it is there. And I wouldn't necessarily even yet get too excited about it, especially since we have a huge amount of run 3 data that we should be analyzing soon. And if we saw then 4 excesses in T Higgs, run 3 and run 2, Atlas and CMS, then I would certainly get excited about it. If we look at these 2 excesses, and then we go back to the Atlas analysis here, we see that those aren't really confirmed by the other experiment. Among all the different measurements that we make, you expect some excesses, so it's not so surprising. It's better maybe to evaluate some global probability, though that doesn't necessarily look so good either. It's 0.01, so that's fairly low. So definitely there's interesting stuff to look at here as we take more data. If we go across the more detailed measurements, it's interesting that a lot of these excesses here, they appear to be maybe coming from some of these more high PT bins. So that's really at least the most interesting place to see it. Hopefully you would see something eventually coming out of that. But one of the nice things here is the experiments were in agreement about these STX cross sections, and they both looked at them. Unfortunately, it's not 100% equivalent. It can depend on the analyzers and how things are being done. Here, Atlas, for instance, is integrating together TTH and TH in their analysis because they don't have necessarily enough signal yet to get a great measurement there. So we can't look at this way of looking at the plot, at least for that excess. It's actually sort of good to integrate those together because the way you do the analysis, they really tend to overlap and be backgrounds for each other. And so putting them together is actually a more solid measurement. But we also want to divide them apart to eventually measure them separately. We do notice in this method of looking at things excess in WH, though not in CH. And if we look though at the high PT bins, we don't necessarily see a repeat of these excesses that CMS found. But I think the interesting message here is that we agreed to do the cross-section measurements this way. And so you could immediately have a confirmation or not a confirmation of whether these excesses are interesting. And without those agreements, then we wouldn't be able to make these exact comparisons in similar PT bins, for instance. Well, what do you want to do with these measurements? This is from the same CMS measurement. You want to look for new physics. So we understand that in general, we don't see some huge excess of Higgs production. We don't see some non-standard coupling to the fermions or bosons. So we have to start looking in specific places. And so you can break down the data in different ways in order to look for excesses. So one is the so-called K constants. So these are generally ratios of the observed measurement to the standard model measurement. And we can see if you look at things that way, that you don't really see any excesses anywhere in this plot. So here you're adding in, for instance, that yes, I saw an excess in W Higgs and Z Higgs at CMS, but I also measured the coupling between the Higgs and the W and Z as a decay mode, H to WW and H to ZZ. Overall, I don't see anything there. But it does give you a hint that if I did want to look for things that I want to understand whether there are contributions that could be on the production side, but not necessarily the decay side. Then you break out into all you can break this down further into various operators. And so there's standard model expectations for each of these. So each of these represents some coupling of various elements in the standard model. And you can look for the contribution of new physics here. So here we're saying that if you see some excess, that it would represent some new physics energy scale. And these are actually the limits that are put on those energy scales. And we see they're going out generally to the TeV level and sometimes up all the way to the 10 TeV level. So we're putting fairly high energy constraints here. Not, I would say, as high energy constraints as some of the more dedicated searches to things, but this now makes sort of a global picture of every operator that exists that can have some coupling that involves the Higgs. But all these operators don't really tell me very much. You tell me that there's a CHI3 operator. Okay, I have no idea what that means in terms of what physics that might represent. So here, just to give you a better picture of that, here are all these constraints on the operators. Here are the new physics scales that are limited. But here, now for various choices of operator values are the effect that you expect to see on the ST, STXS cross sections. So if I increase this CH box operator and I made it 0.83, for instance, then I'd see this purple increase in cross section across the various bins of STXS cross sections I measure. So if I try to look for something that could affect, for instance, the WH cross section, so here are the WH ones. So here's an operator to affect it that actually lowers it, but probably I can maybe take the inverse of that, make it negative, and that might raise it. But then I noticed that if I have that lowering, I also would expect to see an effect over here in GluGluH, and the GluGluH cross section looked pretty much as expected. But you could test each operator this way, and now they have a framework that allows you to do that to see pictorially what the effect of any operator is in all the cross sections that you measure. But that even isn't necessarily the greatest measure of new physics. New physics should be from some UV complete actual model with particles in it that have some definite masses, for instance, and then you map out what the physics is. But if you have an idea of a model, so you're a theorist and you introduce some new physics particle content, and you make those particles part of some group, for instance, and postulate what the various interactions are according to Feynman rules, there are now automated tools that allow you to take that and map it into all the EFT operators. And so it's hard to do the inverse, take any pattern of excesses you see and go to what the model is. So various theorists have some intuition about that. They see, okay, I see these, this might be this sort of model. But now you can take that model and you can map it exactly into what pattern of excesses we would expect to see, and then compare that to the data to see if you have anything. So I would say overall in this picture, we're not seeing anything so excited that calls for you to immediately be doing that exercise. But if we do see a pattern of excesses, we're starting to have the technology that will allow that to map it to what the new physics model is. So that would be pretty exciting. So now you take this and you realize Atlas has equivalent data, and we have 2-3 times more data from the run 3. And so I think we can shrink these constraints quite a bit, and maybe start to see some excess if there is one to see there. All right, so the last thing I mentioned was differential Higgs production. So this is dividing things in slightly a different way. And the idea is to pick some distribution, look at overall Higgs production, and then make a differential fiducial measurement versus that distribution. So here we can see various ones that are of interest. So here's the PT of the Higgs, and here's the number of jets. Down here is the PT of the first jet, and here is the rapidity of the Higgs. So very basic property of the Higgs and things that might be produced with, like numbers of jets, for instance. But integrated over all the different Higgs production modes. So it's a different way of slicing the data. I'm looking at it all Higgs, but in terms of kinematics, I'm not trying now to divide by which production mode I'm looking at. And interestingly, it's really remarkable. Almost exact data agreement, some small deviations, but with the number of bits here completely inspected all across these various distributions. And there are other things of interest here as well, like looking specifically at events with 2 jets is very interesting because that's what you generally see in VBF production, for instance. And so looking at differential measurements that are a little bit more specific like that are very interesting as well. So it gives you another view into the Higgs, maybe one that's a little bit more easy to understand than the simplified template cross sections. It just says overall, what is the PT distribution of the Higgs, or the rapidity distribution of the Higgs? So from those various things, maybe I want you to get this picture that we're really doing a global and comprehensive analysis of the Higgs, probably more so than in any other sort of final state we're looking at. And again, it's because Higgs is a newly discovered particle, and as newly discovered, that means is it was the least investigated and maybe the most likely place to look for new physics. So we're giving it our all to try to do that. So Higgs is not only about its production and decay, but there are also some basic properties that you should look at. So first, I want to talk about the mass. And so both CMS and Atlas have done sort of a final run-to mass analysis. So here's the data set from CMS. So this is all 4 lepton events. So it's sort of interesting. You can see the Higgs peak here. You can see CZ production. So since this is under 170, this is where one of the Z's is virtual. You can see a peak on the Z here. So this is where a Z was created. It decayed to 2 electrons, for instance. 1 electron emitted a photon, which then split to 2 leptons. And so these are 4 lepton events from the Z. And we have great agreement over this whole range. And so this is the area where we're trying to extract the mass from, but we're doing it using our absolutely best measured optics. So we carefully calibrated the tracker and the Muon system to get the best momentum measurement out of it. For the electrons, it's even more elaborate. So I was discussing, I got with Fu yesterday, that if you look at the forward calorimeter of the CMS experiment, we recalibrate the energy scale there using a laser pulsar every several microseconds going through the whole system in order to get a new calibration. And the reason is it's taking so much radiation damage from the LHC that its performance, you can see it degrading in real time, but we're then correcting it in real time. And things like that are necessary to have the energy resolution in order to measure the Higgs this precisely. So if we look at the results here, so here's Atlas, and so that adds up to 11 MeV. We put those together, if I remember correctly, and there's CMS that adds up to 12 MeV total uncertainty if we put them together. Sorry, actually, 120 and 110. And if I express those as a percent, it's 0.1% precision. So remember, the double wave mass, we're actually getting to 0.01% precision. And I think the difference here is all in statistics. So here, the statistical error is 0.9 and 0.10, and systematic errors are 0.5 and 0.6, and those will probably reduce even further once we accrue more statistics and can calibrate better. We should be able to go down to the level of, if we have the statistics eventually, also 0.01% precision for the Higgs boson. And so incredibly precise measurements, not so long after 10 years after the discovery. Typically, we don't progress this quick to making mass measurements this precise. But as you know, sort of the phase space of top quark mass, W boson mass, and then the compatibility with the Higgs boson mass is a big part of the lecture we fit where we look for any possible deviation. And so measuring those, including the Higgs boson mass, is considered very important. Also, in these measurements, we measure the Higgs width. It's incredibly small at the MeV level, so standard model prediction is 4.1. We're not quite, I would say, to the level where we have great sensitivity yet, but we are starting to make a measurement of that. And if you turn these into a limit, that limit is only something like a factor of 2 over the standard model. So we really see that as expected that the Higgs is this very narrow width particle. Quantum numbers. Well, I think we know for a while that it's a spin zero scalar, it's CP even. The evidence there is so strong that it's not even worth giving any plots that demonstrate that. Nowadays, constraining its quantum numbers has moved to be an EFT analysis of whether there's any CP odd contribution in the Higgs. So if unfortunately, if we're in some MSSM and the A directly overlap the Higgs, maybe you'd expect to see some CPI contribution there. Or in some other model where the Higgs is more complex than we think, maybe there'd be some CPI contribution. So we'd like to measure that as well as we can and limit it. So the way to go about that nowadays is you're using EFT. So you introduce operators that have a CPI contribution and then a couple involving the Higgs. And in fact, to get sort of a good measurement here, it's useful to make some optimized observable. So usually you would look for the evidence of CPI in like the angular distributions of the decay, but you can optimize that variable to make it most sensitive. And so an optimized variable was made for each operator that we want to measure. So these are the HW operators, this third one here. And particularly nice is that the authors of this analysis did not just do a search for new physics, but they also made a cross-section measurement, something that can then be compared to any theory that's not specific to a specific EFT operator or a specific theory, optimizing for that. Instead, though in a complex variable that's good for detecting a certain sort of CPI contribution, but nonetheless, they have a measurement in this variable of that, a differential measurement that shows the expectations, the measurement compared to the expectations of the standard model, or a contribution from this operator, if you want to put that in the plot. So they're one of these differential measurements for each of the operators involved here. And then over here, we see the actual limits that are put on these operators. And it's sort of nice because it's comparing here what was gotten similarly from the STXX, XTXS, the STXS. Maybe I shouldn't try to say that. So the simplified template cross-section analysis. And comparing to what's done with these optimized observables. And so here we can see a very nice example of what came out of the template analysis and what we get out of this optimized analysis. And we see that it's a lot tighter in this optimized analysis. So this really sort of focuses on this issue of CPI contributions and optimizes really substantially. In fact, you can see there are actually two dots. So you actually had a base case that had two minimums in it when you did this in the simplified template cross-section analysis. And then that ended up giving a much wider possible window that this operator could be constrained in. And so maybe the most interesting coupling of the Higgs is the self-coupling. So an interesting analysis has been done here, where what you do is you include both Higgs production and di-Higgs production, and you try to extract these self-couplings. So in general, the self-couplings are like this. So here's a gluon fusion self-coupling where you emit a Higgs, but then it decays to two Higgs. So this trilinear coupling is allowed by the standard model. And so this K lambda here is basically, again, the measured coupling, or if you want to look at new physics, the new physics coupling compared to the standard model. But the problem is, if I see HH production, it might also be HH production from this. So this normally would be resonant, but not necessarily, because we know that off-shell Higgs production exists, and this would be more continuous, but they're both HH production, and so there's going to be some overlap in it that makes it hard to disentangle this K lambda from these K fermions. This typically would be a top loop, for instance, and so that would be the coupling to the top. Similarly, there's an interesting self-coupling that involves vector bosons with two Higgs, so it's a quartic coupling. So we'd like to measure the so-called K2V, but it's hard to disentangle from this KV here which comes from just couplings to single vector bosons. So here, there's not even this resonant phenomenon necessarily, because in this vector boson scattering, you could make these two Higgs to be more on shell, for instance, just like you could in this case over here. And so here, as illustrated a plot, this is the one that actually comes from the analysis just of the Higgs production, and it's showing K2V against K lambda here and the constraints on that. So this is the standard model prediction. What is measured, you can see they're compatible, but these ellipses go over some fairly large ranges here. The different ellipses are from different A modes of the Higgs. So looking at EV bar plus tau power, gamma gamma, and other things. But you can get a better constraint of this by at the same time looking at single Higgs, because that allows you to, for instance, directly constrain some of these overlapping parameters. And so if this K fermion is giving you a problem in determining what K lambda is, and if I can separately measure K fermion in single Higgs production, then that helps me to constrain it. So here in spaces where I compare K lambda against K fermion or KV against K2V, I can see, for instance, in this case, that from the double Higgs analysis, which is sort of in this brownish yellow color here, I don't constrain K, constrain K at the top very well. But when I do this combination with the single Higgs, then I do constrain that K top well, and then that tightens up what the constraint on K lambda is. I go from K lambda being from here to here to tighter constraints, for instance, the red one here. And similarly here, I don't have this sort of unbounded constraint of K2V as I did for K top here, but I do have rather big ellipses and a rather bad constraint on the KV axis. And then I tightened up those constraints when I do the combined analysis. So again, moving to the more global picture, where I combine lots of things can be very, very helpful, because these couplings may occur in various places. All right, I just have one more topic to cover. And so this is the Higgs rare processes. So we've been looking at this picture where we see some deviations, but they're not really always confirmed by both the experiments. Really, the one that exists is sort of the single top Higgs deviation, but otherwise, in a lot of different ways, it's a pretty consistent picture with the standard model. And so the question you would ask is, what more should we look at specifically? And one way to think about that is they ask the question, what is still fundamental in Higgs physics, which we haven't yet addressed? And so this is a place where understanding the structure model, standard model, tells us very exactly that, yes, there are very interesting things to still probe in the Higgs sector. So one that I've mentioned a few times already, but that we'll look at specifically here, is the coupling to the second generation Yukawa, the second generation particles via the Yukawa mechanism. So we see already in this picture that things seem to obey the Yukawa mechanism, but it's completely dominated by the top and the B in terms of the fermions, and the tau in terms of the lepton part of the fermions. And so that's all the third generation, where we already see that there's a strange spectral relationship with the top. And so you could imagine that maybe there's something that divides the other generations. Certainly, people would say there's probably something that divides the neutrinos, and they might be getting their mass from another source, because it's hard to understand why it's so many orders of magnitude down. But I would say that about the electron as well. The gap between the top quark and the electron is just gigantic, so that they would get mass from the same mechanism, but by constants that are so many orders of magnitude apart, seems rather strange. So going to the next generation is very interesting. Going to the first generation would be very difficult. Just coupling H to EE, for instance, is just so tiny. And then the other area, we've also already looked a little bit of it, is multiple Higgs production. Because multiple Higgs production, it tells you about things like the Higgs trilinear coupling. And it's those couplings that actually define the shape of the Higgs potential. And so we understand that already that we're in possibly a strange area of that potential. The default fit says that the universe is actually in a metastable state, not a stable state. It doesn't do that with particularly high significance. And metastable state usually means times on the scale of the universe long before you decay into the other state. So then, in a public lecture, someone asked me, well, what does that mean? Well, if we're in a metastable state and we decay to the other state, that means that all of a sudden how the Higgs interacts with the W and Z bosons change completely, and probably means that everything is instantaneously destroyed. So I'd prefer to be in a stable state, even if it means, even if metal to a stable state would be billions of years, there's always some probability that you actually have the tunneling. And so third generation first. So our biggest success, sorry, second generation. Our biggest success has been in H to mu. So here we see evidence in the 13 TeV data that we've seen this decay. It gives you, since it's sort of right on the edge of evidence, an idea of what that looks like. So here is the plot here of the mass distribution. These events are actually weighted by how significant they are. Or any set of momentums, so we could weight the plot by that, making the events that have higher signal background show up more. And we can see here a little peak, and the error bars are also pretty small. So in the end, it's a significant peak. We see evidence for H to mu. So then you can do a combined fit, because we have a lot more data on this as well. And you extract this coupling constant for the coupling to the muon. And so we can see that it's very compatible, even at the 1 sigma level, well compatible with the standard model expectation, that's 1. So I would say we pretty strongly confirm that a next generation of things couples to the Higgs as expected, but there are very big differences between the lepton sector and the charged and neutral and the quark sector, so you'd like to get this in the quark sector as well. So here's our progress on H to CC. So H to strange is probably inaccessible. I'm not sure you could even do that at a lepton collider. But H to CC is something that we can do. So I would point out that this is really driven by the just outstanding performance of the B and charm taggers that we built that just amalgamate an incredible amount of information, including partially reconstructed decays and all the kinematic information about everything in the jet that you're trying to identify as a B or C jet, and get these really surprisingly high efficiencies for identifying these things. So as a proof of principle here, we actually usually do a simultaneous analysis. So if you're looking for HW or HZ production, and then you're looking for H to CC, you also have H to BD there, and so you can make a comparison to that. But in addition, you have ZZ production, and you have ZZ and ZW production, where the Z also has a substantial branching fraction to C quarks. So you can look for that. In fact, it's something important to understand as a background to Higgs. And so here from Atlas are these measurements in WZ, ZZ, and then the combination of the two of them. And you can see, especially over all the 3 modes together, they get a pretty good measurement. Look at the errors here, 25 and 22%, so really significantly different than 0 and compatible with one of the Z to CC. So that means that work to make that incredibly powerful tagger and calibrate it so you understand its efficiency correctly is working. And so then we go ahead and do an analysis with that. So this is the analysis of VH for Atlas. So this is the C results. And these are limits compared to the standard model. So expected to get a limit around 10 and instead see something about 11.5. So we're pretty far from the standard model soon. With root-in progression, you might see you need 100 times more data to get to the standard model. But 100 times more data, this was just 100 inverse, order 100 inverse femtobarns. So you go up to an attobarn, that's 10 times more. You go to 3,000, that's 30 times more. And so we're 1/3 of the way there. But we always tend to combine that with improvements in analysis as well. So maybe it's possible to bridge this gap and start to be seeing a slight signal for this process. So here's the analysis from CMS, and interestingly, it includes TTH, which actually is such a distinct signature that it turns out to be a powerful mode. And so in fact, the expected significance here was 5.6 times the standard model, even though we observed higher than that. And the expected significance of combined here. So separately, the expected was 8.7 and 7.6, and you combine them together, you get 5.6. But we saw an excess actually in VH with H to CC, not one necessarily that's compatible with the standard model expectation because it's up here at 14 times the standard model. So it's probably just this statistical fluctuation. Notice it's within the 95% confidence level interval of what you would expect. So I would pay more attention to the expected limit at 5.6 because going forward, as you take more data, that's hopefully what you would continue to achieve. Then you're only 5 to 6 times more times the standard model. You need 36 times more data. That's within what we expect from the LHC. So if Atlas can do as well as CMS, then you'd actually get a factor of 2 more than that. I think you're really in the range where we have some potential to measure this H to CC. And so that would give us on both the fermion side and the lepton side a second generation measurement of the Yukawa coupling. And that I think would pretty much seal the deal on saying that the Yukawa mechanism is what gives the mass to the standard model fermions. Except, of course, probably the neutrinos. The neutrinos, usually there are other methods that are proposed to explain that. So the last rare thing to look at is H8 production, and probably the most interesting. That's why I left it towards the end of this talk. This is the thing that will allow us to map out the standard model potential. Maybe one of the most important measurements that can be made at the LHC. And so here I'm showing the Atlas and the CMS results here. And so we combine a huge number of modes, but actually we're dominated by having either a large branching fraction or in addition having a distinctive signal to look at. And so the dominant modes are BBBB. So B quark can be hard to distinguish to other things, but once you have 4 of them, it can become pretty obvious. And so that's a powerful mode. And it's also one of the larger branching ratios of the Higgs. And then BB gamma gamma, so it makes use of that large branching ratio, but then the very distinctive and well-measured gamma gamma signal. And then BB tau tau. So having 2 taus also gives you not as good, but still a mass peak, and it's a distinctive signal. So that does very well. In fact, it's the best of the expected limits here. But we throw in anything else that we can. So multi-lepton is lots of different modes with W's and Z's in them, for instance. Or similarly with leptons and B's and missing ET, we combine everything together and we're at the level of expected 2.4 times standard model, observed 2.9. So I'm completely speculating now, but my bet is that if you gave an expectation of the standard model with signal here, this is sort of compared to null hypothesis, that a small excess when you're at order sensitivity 2.5 times the standard model is starting to be expected at this point. but nothing significant compared to how close it is to the expectation. Atlas looks very similar. So also, so let's see, a 2.5 expected compared to 2.4 CMS, 3.5 observed, but also very well within the expectation that we have at this point. So I combine those two together, divide by √2, and I'm somewhere under 2, maybe a 1.7 or so. And so to be putting limits on standard model production, I'm probably just an analysis of the full run-through data of the date away from that. An incredibly hard analysis. This needs accurate calibration of every single part of the detector. It's probably not something you're going to see at lepton photon this year, for instance, but it is something you might be seeing next year. So that's quite exciting, because not only are we going to get to the level that we could put a limit on the standard model, I think we'll fail to do that because we're probably going to observe something, but that means that with another doubling of the data beyond that, or a little bit more, we're starting to get to the level where maybe we can see evidence for this. And so this is looking now like something that we can definitely measure at the LHC. If you look at projections from, let's say, 5 years ago or so, they didn't look as good as this. And it's because we made a lot of progress in improving the analysis. And we might get a little bit more out of that and all the additional data as well. So HH is definitely something I think we're going to do. I don't know if we get the 5 sigma, but I think 3 sigma is pretty easy. Then here, this is the analysis that actually produces these constraints in the trilinear coupling and the diacritics coupling to the vector bosons spaces. And so here I show both the CMS and Atlas ones. I tried to get the lower axis to a line here to demonstrate that they're pretty similar to each other in terms of the constraints that are being made right now. Of course, what you'd eventually like to see is a constraint that, for instance, does not include 0 here on this axis. Clearly not quite there yet. All right, so summary. So something that you may have noticed along the way here is basically every basic, like up to 2 or 3 Henry particles, standard model, but also standard model plus QCD, because we have a lot of these measurements with jets as well. Final state that you expect to see at the LHC, we've made measurements of that. That makes us be able to make these remarkable global analyses overall the data at LHC. So not shown here, but there are also, for instance, this EFT analysis that span all these groups. Those are connections between them. So what I talked about, what Reinhardt talked about, and QCD and other things as well. Our highest precision measurements, or best precision ones, have gone to the 1.5% level, and I think 1% is completely within reach. The main limiting factor there, the luminosity uncertainty, has already been solved, basically. So we just need to get those measurements out using those luminosity determinations. Our measurement of sort of fundamental parameters, so things that have been measured at previous experiments, like the W mass or the effective weak mixing angle in the electroweak scale, are becoming competitive. We're like % away from previous measurements, and we'll exceed them with the next round. We've really seen the complex gauge structure of the standard model and its coupling to the Higgs and everything. We've seen vector boson scattering that involves the Higgs. We've seen all these multiple boson interactions, and similarly, a big array of interactions that involve, for instance, Higgs bosons and vector bosons. And so all the structure that comes from the gauge group of the standard model and from electroweak symmetry breaking, we've explored all of that. We don't really see any substantive deviations from the standard model. But on the other hand, we do see deviations. They're often in states that are either new, or they involve multiple particles, multiple vector bosons, multiple jets, multiple Higgs bosons, for instance, or Higgs bosons with other particles. And what's sort of exciting is that the calculations and techniques that we have for probing those difficult sort of final states are improving so fast that I think if we get to the level where we see a really statistically significant deviation, that we're going to have the theory necessary to say whether that's new physics or not. And so I leave you in conclusion here just with a sampling of the important things that have been done. So the most precise measurements, the most precise precision measurements of W mass, things like longitudinal vector boson detection in vector boson scattering, and of course the Higgs analysis. Okay, thank you. I have a question from the usual source.
The simplest concept of things. Structure was two Higgs doublets, three of the Higgs get eaten by the WZ, the leftover with one Higgs scale. The Higgs scale is very massive, most massive elementary quantum except for the top one. Is it possible anymore that that's just the lowest mass Higgs? That there are higher mass Higgs particles be discovered?
I mean, absolutely, right? We're
Well, but you're doing so well with that minimal model. You're fitting everything so beautifully. One single Higgs scalar. If you added more, will that spoil that good agreement that you're getting already with only one?
But I would point out sort of the interesting hints that we have. So dark matter, right? So, you know, I look for a simple dark matter theory, and you know, the simplest one that comes to mind, not so simple, but supersymmetry. But it proposes more Higgs bosons. If I look at the unification of the forces, something I would like to see, and do this projection to energies like the beginning of the universe, the standard model scenario, they don't quite match up. But you add extra symmetries that have extra Higgs bosons, and you get those things to unify together. So, I mean, I think all the hints are there that there should be something. And the question is, what can we do with the LHC data? Or what accelerator do we need, for say I'm in favor of the muon collider, in order to get to the energy scale to see those things? So they're there to be found. And it doesn't matter of figuring out how. It's neutrinos. Yeah, this is an argument I have with my colleagues from Lansing. They incorrectly always say that the new physics beyond the standard model has been found and correctly measured and neutrinos. It's not a very big change in the standard model. It's sort of minimal way to include them. I mean, maybe we should really, but we don't know which of those models is, which is why we don't have a new standard model. When I look at neutrinos, I like to look at the things I think are more exciting there. So if I look at the mass patterns that are implied by the the mass squared measurements we have, it looks like it almost might be an inversion of the matrix that you would expect that would create the masses of the fermions. If I look at the pattern of CP violation, the hints from the T2K experiments and so on are that CP violation is maximal in the neutrino sector, where it's minimal really in the quark sector. And so there, you know, these give you some hint that maybe there's some overall mirror image theory that's sitting there. So I mean, I think we don't quite say yet that neutrinos are the ultimate evidence of beyond the standard model physics, just as we don't say necessarily dark matter effects. We don't understand what it is today. Not that it isn't unambiguously on physics.
Stick around, I'll make a big deal about that Tuesday afternoon.
Sorry again?
Stick around, I'm gonna make a big deal about that.
Well, I don't know, the students have any questions first? Any questions or comments or?
Well, let me ask you something. So,
First of all, I'm very excited about this idea that now we can put together many measurements and extract multiple constraints from multiple experiments with multiple parameters. And then if we go, of course, do that, of course, the statistical analysis becomes very, very massive, very, very complicated. For example, let's go to slide 61. Right, so we do something like this middle plot. We do some scan on some coupling parameter, or maybe several of them, and then we look at the what you call the -2 delta log likelihood. We call it delta chi-squared, and then we extract p-values. And of course, when we do the scan, we can keep parameters at the standard model value, or we can allow them to be anything, or can allow them to be in 60% confidence region. But the question to you is this delta chi-squared equal 1 criterion really acceptable in the scans? Because, for example, the PDF analysis will say it is not. It's too constraining. So it gives you a small error, but if you have tension between experiments, for example, or you have different models of PDFs, the result will be elsewhere. So
I mean, my feeling, okay, maybe not this constraint, which actually tried to leverage all the other modes as well, and thus became more complex. You know, but otherwise, you know, there's a constraint that's just based on the H2U here, but everything is statistically limited, and it's not very different from this. I would say that one is completely reliable because it's just completely driven by statistics. So, you know, I would say, you know, you would more question, you know, exactly what you were saying we should get excited about, which is that, you know, we have these global analyses where this is all very theory informed. And I think we have the same evidence that you do when we try to do this. If you look at the CMS, WMS analysis, what we find is that we have to inflate the PDF errors arbitrarily actually to get a good agreement with our expectations. And even worse, you know, these are all, since there are so many uncertainty distributions to sample over to figure out where you are in the likelihood space, we're sampling them using Monte Carlo techniques. So we assign some probability that what we've observed is compatible with data. But the space is so big, we're not sampling the whole space. You know, we're using these Markov chain ideas to hone in on the proper part of the phase space. But it could mean that the full map is a lot more complex than what you expect, and you put some expectations in. But on the other hand, it's good because it means that in cases where you put a theory error in and you understand that it is not calcium at all, there's no need to sample a calcium distribution there. Typically we do, but Monte Carlo techniques, we emphasized yesterday, they give you the ability to address sort of those things. And interestingly, it's so complex now that the limiting factor is computer power, but the computing power is getting better. So I think we can go a level beyond the concern you're expressing, you're seeing, for instance, in the PDF is. But, you know, we'll go a step beyond, and we'll realize there's another step we can go as well. But we should improve that because we really rely, for instance, on the PDF constraints now for a lot of measurements, and we see the weaknesses in this huge amount of thought that goes in it, but it's so complex we realize it's not perfect. And I think that's sitting there, you know, when we perform, for instance, the top mass combination, we get the same problems on the experimental side, the space of uncertainties there is so complex, you know, so understanding, for instance, let's not do the math, let's do the cross section. Understanding the correlations between the CMS and Atlas luminosity measurements, which are correlated to the LAC, those, you know, are extremely complex and usually done wrong on the first iteration through.
But yeah, I think this is not just some abstract exercise, but for example, you can ask very fundamental question: is the vacuum metastable or stable? And then, but we need to compare several parameters at once.
Yeah.
And then the question again that I have, whether it is possible there is still a solution somewhere in the LHC data that allows the vacuum bit to be stable, maybe less stable. And then it will depend on the definition of these errors that we.
And sometimes we introduce dependencies for theory that we don't really realize till later. And you remember these original measurements of the Higgs width that use these off-shell interactions of the Higgs, to constrain the width on it. But immediately come back, there's a lot of criticism that you're introducing some very strong theory input there. And so, when you come up with a distribution of the likelihood of what the width is, it has some arbitrary theory input that's constraining that distribution, and that needs to be understood. So, I think the Metascape will stay in your list, probably even more mixed up and things like that.
Yes, I agree. Yes.
Let's just wait and see.
But now I sort of stay.
Okay, no other questions? Let's thank Matthew again, so. We have great provision at start as well, 1:15, so.
And I think today you can just leave the bags here because the whole building is closed. And I think, again, when you come back, so we have to keep the doors locked. But we'll put someone who will sit by this door, and just open the window,